This is what we're going to be making from scratch inside of the Godot engine, and this will be useful for any 3D game. Here we have a bunch of different effects that's going to allow us to detect collisions against the mouse. This is a axis aligning bounding box, which is called AABB. This is an approximation of what a AABB would look like, and this is not what we'll be doing on this tutorial. And this is a 2D rectangle that we can use to calculate AAB points or mesh points to encompass it. And as you can see, currently it's using the AAB example to encompass it. And why are AABs useful, you might ask? They're used for collision detection and are faster than physics calculations. AABBs are basically a set of coordinates with 2 points that are being used to create a box, a start and a size, which should encompass your geometry and allow for different various operations, allowing to check for collisions against points, rays, or other AABBs. Such are the methods inside of Godot here on the AAB class. And we have here intersection with other AABBs, intersection against plane, intersection against rays, and if it has a point inside of their volume. So this will be useful for basically any 3D game you are making. You can use this for damage dealing, for item pickup, object placement, and object detection. Think about it like a 3D version of the rectangle tool. In the case of my RTS project, this will be very much useful. And also, as a bonus, we'll be doing this green rectangle effect, which allows you to encompass a given AABB or a mesh. And initially, this was the effect that I wanted to achieve inside my project. And because some methods overlap for the two different things, I decided to include them inside a video, but I'll probably split them up to be easier to find on YouTube. Important to notice that this is the AABB we are going to be building inside of the engine, and not this gray square, which is the AABB. Godot does not have AAB collision detection methods. If we wanted, we will have to build them from scratch, and inside of the GDScript language that will not be performant, as AABB methods are compiled on the C++ side of things. But we can simulate this AAB collision effect by using the intersect shape function from the physics server. We have a function for the physics directed space state 3D, which is called intersect shape, and this is being used for every 3D nodes. And we can use this to perform that kind of calculation for the AAB effect. But keep in mind that maximum results are allowed to 32 hits. The main benefit of using AABBs is performance, because AABs are only a set of coordinates, which also means they do not handle rotations. As you can see, the box stays aligned to the axis every frame. It is being calculated using the mesh space, but it does not rotate again with the object. So, with this information in hand, let's see how we can build these AABBs. So this is going to be the project that you'll get access to if you support me. So this is one that is going to be available for YouTube members. So let me just update here the code. You're going to be able to access its functions and everything you want. And here should also be part of the tutorial, and I'm just going to let everything to be visible so you can actually see all the things that you're going to be able to access. So we have here everything we talked about in this tutorial. We have access to a localized version of the AABB, the bounding box simulation for OAB, the rectangle, and the finalized AABB. So that is what you get access towards to. This is part of the final project. The free one is not going to have any of it. And also this is going to have the high version of the statue as the node here. Now for the purposes of this tutorial, I am going to change a couple of things here. The first one is I'm going to duplicate this main scene, and I'm going to strip away most of the things that are already built. So now we are going to be editing this new scene, which we are going to be making some changes. The first one is that I am going to want just a single debug square, and I'm going to call this debug AABB, just so we make things a little more simple. And as well, let me just change the material here to make it unique, and let's change its albedo to be a greenish color, so we can differentiate from the other stuff that it is already in the tutorials. As well, I am going to change this statue script here. Let's actually drop a low poly version of that statue. So let me see which ones we have. We have this one, and I think I'm going to use this one. So this is a low resolution version of this statue. All of these assets will be inside of the project. So let's use this one. Let's delete now these ones. And actually, I want to keep the animation stuff, so let's make it local. Let's drop the statue inside of our square. Let's delete the high poly statue and the extra node. Now we only have the low poly statue, and then let's rename to make things simple. Low poly statue. We're going to access its material and simply, so it's inside of geometry, my bad. So here inside of the geometry, we have a property called transparency. Let's turn this all the way up so we hide the actual mesh. And we have to remember that this is just a helper node because I have some animation that we're going to be using. So if I select my animation player, is the simple moving around so you can actually see the AAB with its current status. So let's leave this animation, so let's not delete this node. And we're going to be accessing the scripts, and I think I'm also going to duplicate the script for this. So the script for this one is main tut, which I think I already did. Okay, so this is part of the scene script, as you can see on the top here. So let me just save this one so you can actually see it. And let's say main tut script. We actually know that this is the one we want, and I think I do not want it to be TRES. Let's just keep it as GD. There we go. And by doing this, now we have the things we need. So let's just rename this to be, let's leave it AABB master. Why not? So I think this is all we are going to leave it out. Let's fold the map. We have our debug AAB, and we're going to be doing the AAB code. So that's about it. Let's open the script here. So of the things we need, we have a variable for the current camera, which is used to snap the camera. So I believe if I run, it's going to have a bunch of errors because of the different things we did with the renaming and stuff. So for instance, debug no longer is that. It's called now debug AABB, and that should fix most of the things. We do not have this one. So let's delete. It's going to put the code where we don't have it. So let me just erase this one. So we don't have these ones. So let's just hide this code. I'm going to delete everything. Yeah, so we have stripped away some of the parts of the code. So now we should be generating the AABB for this one. So the code we have here for this script, most of it, like these ones, is to switch the camera. So whenever I click, it switches. That is also why I have this variable here. So we have here a script which we are going to be building from scratch, which allows us to calculate the AABB. This is the main script one, the statue, the camera, and the cameras we wanted to switch to. So I think this one is only the relevant one for this tutorial. We have the debug AABB square, and we have the mesh rectangle nodes. So most of this code is for the statue. We have a code here on the physics process that allows to rotate this node. This script is on the AAB master. So this one will keep rotating on this way. So we have some visual effects to also see how the AAB reacts. So there we go. You can see that this statue is rotating. That is because of this code and is running on the physics process. And the function that is calculating the AABB is this one right here. So, and this is the one we're going to be analyzing here. So I'm going to delete most of these comments here that we no longer have, and also that one. These ones I think we can also keep. And yeah, that's about it. So let's just as well hide the rectangle, the rect2, because we don't need it anymore. And let's leave it at that. So as you can see, it's pretty simple here. The main function that is returning the AAB1 which is this one, is from our AAB calc variable, which is our main AAB calculation script. But we are going to be doing this from scratch. So as you can see, there it is. So if you run the scene, this is the stripped away version that we are going to work on. So we already have the AABB working. Let's actually open now the AAB collisions like this one. So this is the main code that we're going to be replicating. And I'm going to be building this from scratch so you can understand. So let me just duplicate the script and call this main one for tutorial. This is the one we're going to be working on. So every function from the public ones we're going to be deleting. That's right, we're going to start from scratch. And that should be about it for us to start. Now let's just update our dependencies. So let me go to the script here for our AAB master, and I'm going to actually close the other references because we are not going to be using. It's going to be still inside of the project. It's just for us to see what is going on. And let's just update this one right here. So this is now called our AAB main tutorial. And of course, now because we have a blank script here, it does no longer have the function we need. These were the dependencies we were using. So we have getRec and getGlobal AABB. So let's build from scratch these functions. So let's go to our AAB functions and let's start coding here. Okay, so the first function we're going to be building here is the main one that we'll be using to return a AABB globalized to our mesh. So I'm going to actually do a very simple test here, and I'm going to be retrieving our AAB from the current mesh. So instead of using the special function, I'm going to simply do on our statue, I think. We're not going to do on the AABB master, so let's do on the statue. So our statue is also a little different here. So this is the statue code which we want, and I'm going to do here that variable dot get mesh and dot get AABB, and this is the one of the ways you can retrieve an AABB. There's a part of this code that I also do not want right now, so let me just comment these out, and just to make it a little different, let's comment these out. Okay, so now we have the basic AABB. Let's also hide these ones, and yeah, I think that is our starting point. So as you can see, we have statue.getMesh get AABB. So the first thing you want to do is to update our debug mesh to be the size of our AABB. So this is the one we are doing. So we are getting the debug AABB as we are getting its mesh as a box mesh, which is this type. So we have access to its size, and we are setting its size to be on the same size of the AABB. So just by doing this, let's run our scene and let's see what we have. And as you can see, our square now has updated to the size of the AABB of this statue mesh, but it does not move when it's positioned. So we can actually start testing this by doing if our AAB mesh intersects with array. So this is the code that actually does the collision detection for the mouse. We have here some variables that we need. So for instance, we have the mouse position, which we can retrieve by getting the viewport, getting the mouse position. We also need the current camera 3D for the codes down here. So we can retrieve the current 3D camera by getting the viewport and getting the actual 3D camera, the current active one. And we need a ray from and to, so where the ray starts from, we want the ray to start from the current camera and be giving towards the mouse position. And we want to create this in 3D, so we do a project ray origin and normal. This is part of built-in functions that allows you to do this, and it's very common to do this. So we have here the stuff we need to actually be calculating the mouse position against the AABB, and we simply does a intersect ray with the ray starting from the camera origin towards the ray orange normal. So whenever the camera is looking, we're going to cast a ray from the center of the camera towards the mouse position on the current viewport as in the 3D camera, and it's going to create a 3D laser beam basically, which represents the mouse position against the center of the camera, and whenever that touches the AABB, that laser will go through the AABB. And if that is the case, if we are intersecting with that laser from the mouse, we're going to simply turn the visibility off of the AABB. So just by doing this, and let's see if I can switch the camera. So we are no longer seeing the square. So what is going on? Let me just update this position to be somewhat closer here to our scene so we can actually start seeing some stuff. And as you can see, whenever we pass the mouse, it's going to turn it off. And also, I forgot some of the code here, which is to always keep first the visibility true. So because this is a running in the process function, this is being run for every frame. We are turning the visibility first on, and if we intersect with the laser beam from the mouse, we turn it off. So that was why it was always off. So now it should switch on and off. And one of the things you might notice is that it's not whenever we pass the mouse, it's around the middle of the scene. So the reason for that is because AABBs are given in local space. So if I put it as far, you can see that whenever we pass the mouse on the middle of the screen, it's going to turn that visibility on and off. It's because AABB's position are given in local space, which means that this AABB position starts on the middle of the scene, despite the statue being here. And this is actually a representation of the AABB, if we do not rotate the object, that is. So as you can see here, the bounding box, we have its position on the center of the statue, and if we move the AABB with it, whereas when we retrieve through code, that is given on local space. So as you can see here on gate AABB, this returns the AABB mesh in local space. So why is that important? Because its position is not following it up. That is why we have this code here, which allows us to update its global position to the AABB mesh get center. However, this was part of the old code that returns a globalized position. We can simply simulate this by doing the global position of the statue. So we can do statue global position, and this should actually fix it. So now whenever we run, you can see what happens. However, as you can see, the AAB position is still on the middle of the scene because we only did move the square one. So as you can see, and the offset is also wrong. This is the part where we actually need to start coding a globalized AABB. So the thing that I'm showing you here is just by using the default AABB, that is the behavior you get. So we need to recalculate the AABB to follow the mesh, to be globalized on its transform, and to update its size whenever the mesh rotates. So this is what we are going to be doing on the main script one, on this one. So the main function we're going to be doing here is a static one, which is going to be get global AABB. And this one, we are going to need some arguments here. First, we are going to need a object mesh, which is going to be a simple mesh, so we can retrieve the AABB, and we also need the object global transform. So we are also going to pass here as a second argument, and it's going to be a transform 3D. This function is going to return us a AABB, however, it's going to return it globalized. And let's just put here to return a new AABB so we can sufficient the function return values. So, okay, we're going to use this to get a new AABB. So let's copy this one and let's update here. So whenever we retrieve the AABB from this mesh, now let's actually use the code from that script, which should be this one. The first argument being the mesh, the second one being the transform, and this is going to return a globalized AABB. So the AABB calc here is just a preload function for on script. So this is the script we are using, and this just preloads it so we can actually calculate it. As you can see here, this is the function we are using. So that function now should return AABB. So let's start to code the action master AABB function. So the first thing we are going to need is to save and store the global position. So we know that the AABB is given local space. We are going to calculate its expanding based on the mesh. Then later we're going to return to its origin. So let's just now save the global position. So this is going to store the global position of our current transform as a separate variable here. Next, I just want to set its, so now I am going to reset that global transform origin back to 0, so we can actually start calculating. So now let's grab the mesh vertices. So this is the code that is going to grab the mesh vertices. So this first line here is allowing us to access the surface tool, which is a helper to create geometry. And we're going to use it by creating a new mesh from our object mesh. So the create from function will create a vertex array from an existing mesh. So we are basically going to be creating a new mesh so we can retrieve its point, and we're going to iterate through its vertices. That is what this code actually does. Next, we are going to apply the transform and set the vertex to form the AABB. So here we have a starting point and a ending point. So for every point inside of our 3D mesh, we're going to first grab it from our vertice array we have grabbed from the mesh, and I'm going to multiply its transform to its point. So this is the part of the code that actually allows us to grab the current rotation of the object, the scale, everything, and apply correctly to our given point. So our mesh was previously in local space, now it's being multiplied by our transform. And here it's important to notice the order of the multiplication. If we change this to be multiplied later, so if we change the point to multiply by our object transform, is going to give a completely different result. So transform and matrices multiplication, you have to take care of its current position here on the code. So the order matters here of the multiplication. So we are going to basically be iterating to x, y, z. If the x start is higher than the start we already have, and if that's the case, we are going to be setting that start position to be the point position, and we'll do this for every angle. So basically what we are doing is setting 2 points here, a start and an ending vector, and we want this to be the starting point of the bounding box and the end point of the bounding box. The way we do that is by iterating through each vertex, and if that vertex, if the vector is higher, we're going to be expanding that vector until it closes. So the point that we have here setting the start of this bounding box to every point if it's higher than the given start, and if the end is less than the given end. So this is basically creating the bounding box and expanding for every single point, doing this for x, y, and z. So now this is the point where we're going to do some math here and actually return the new AABB. So now we can delete this code and see what is up. So we are going to now build a new AABB, which we're going to return it. This AABB is going to start for a current given position, which is going to be the start position that we saved here as a separate vector, and is going to ask for a size. The size is going to be minus with the end and minus the start. This is the way that we are going to be building the bounding box for this AABB. And the position of this new AABB is going to be its current position plus the global position we stored previously here of the global transform minus its size. This is one of the ways that we are setting the offsets and everything to be current displayed. So just by doing this, we now have access to a globalized AABB. And now if we run this code, we're going to get the following effect. And as you can see, we already have built the globalized AABB. It is actually that simple. So as you can see, that is how we do it. So yeah, pretty cool stuff that you can actually do with just a simple lines of code. So this is how you get a globalized AABB. Now, it's important here to note a few things. One of them is that we set the debug AABB, so its global position was equal to the AABB get mesh center. So this is our current AABB we get from that function, which returns a centralized position. These are the offsets that calculates that. So depending on the start position you want to have this mesh, you need to calculate different offsets. As you can see, for this debug AABB mesh, its position starts on the middle of it. So that is why the AABB get center works. If you need other types of position, you can access the AABB and ask for position or a size. So the position is actually the start position, which is the orange point of the AABB, and the end one is the last point, which is the position plus size, or if you need just the size, this is the way you can actually get it. So depending on the mesh center coordinates and also the origin of the mesh you want to display, you need to calculate different offsets. Because this mesh is centralized, its origin is actually very simple to calculate it. And we are also updating its size to be equal to the size of the AABB. And that is how you calculate the AABB. Congratulations, it's a very simple thing. Now let's calculate that rectangle you saw there on the script. So let me just unhide that. And now I think our rectangle is not going to be working. So here we have the rectangle node, and as you can see, this is the one. And if we run the scene, it should be on the top here. You can see there it is. So how I can update this to be inside of our node here? Let's open here the script, and we're going to be creating a new rectangle too. So let's calculate it based on the rectangle on AABB. So this is the function we're going to be building on here. So this is going to be a static function that's going to be the get rectangle on AABB, and we're going to need a couple of arguments here. We're going to need a given AABB so we can calculate it. We're going to need a camera so we can project the points and set the rectangle too. And we're also going to need a mesh node so we can actually grab its global position and globalize all the coordinates. We also are returning a rectangle 2 from this function. So let's do return a rectangle 2. And of course the return here is wrong. Now for this function to work, we're going to need a couple of things. The first one is we need the AABB points. So let's just grab now our function needs. So the main one is we need to grab all the points of our AABB, and we need to unproject all the points towards the camera. And as you can see here, we are grabbing the unproject points from the camera using the mesh node and returning from the AABB points. So how we can grab the AABB points? So we know we have a point for every single one of them for the given AABB, and we need to calculate it. So this is the function that I made that actually return each vertices of the AABB one. So we simply ask for a AABB, so we can actually return an array of vector trees, which is each single point of the AABB. And the way we calculate that is by creating a new array of vector tree and setting its size to be 8, which is for each vertex of the cube. The first one is the position, then we are going to iterate through each one of them. So we create a new vector for each one of them, and this is how you can grab each corner of the AABB one. We'll grab its AABB position, which is this starting point on its x value, and this is what this function does. And all of that is just for every single corner. And as you can see, to simplify this, we have the starting position as the AABB position, which should be on one of the bottom one, I think. And the last one being the end, which is one of the top ones. And we are returning this as array of vector 3. So it's suffice for this part of the function. Now we need to unproject all of those points towards the camera, so we can actually update the rectangle 2D towards those given points of the AABB. And for that, we also need another function. So let me just paste here. And this is the function that gets an unprojected set of points and returns it as an array of vector 2s. So we need a camera, a mesh node, and also the mesh vertices. We're going to be iterating and unprojecting its points. So we are going to grab the camera position 2D of each single point. We're going to do a mesh to camera 2D points. So we're going to create a new array of vector 2s, and we're going to set its size towards the mesh vertices size. So for every single point inside of the mesh vertices size, we're going to simply set its new point on its index to be equal to the camera on project position from the mesh node to global coordinates on its mesh vertices. So we grab the mesh vertices on the current Y we are using. So this is going to iterate for every single one. So it started from 0 up until 8. And I think it's through 7 because it started at 0. And we're going to set a new position on our array of vector 2s. And it's going to unproject a given position, which is the mesh vertices converted to global position of the mesh node. That is why we need the mesh node argument here. And after everything has been built, we have unprojected all of those points. We're going to return it as an array of vectors too. And this is how we actually get the rectangle tool of a AABB. Now the last thing we need is to return a clipped version of all these points towards the screen. And for that, we also are going to be building a new function, which is going to be the get rectangle on a given set of points. And I also made a new function for this. And this is going to clip all of the points towards a given camera if they're also visible or not on the screen. So for that, we're going to need a set of unprojected points, which is the 2D points for a given 3D vertice mesh and the camera. So this is going to calculate if it's not visible or not on the screen. We'll start by giving a new rectangle tool and check if it's visible, which is by default false. So for every single point in the unproject position points, we're going to first check if the camera viewport is visible rectangle, which basically means the current viewport in 2D has a given point. So if any of those unprojected points for our current 3D mesh towards the camera is inside of viewport, we're going to say that yes, we are visible on the screen, so we can actually calculate the AABB rectangle. And we're going to break out of this loop. So now we know that we are visible on the screen, so we can start to calculate the rectangle on the screen. So if that is not the case, then we're going to simply skip this function altogether and return a blank rectangle tool. So this rectangle tool will be scaled towards 0 and will be basically hidden. If that is not the case, then we're going to first set its rectangle position to be the first unprojected point. So if you are visible on the screen, we're going to teleport this to the position towards the first point we have unprojected from the 3D vertices towards the camera. Then we're going to calculate the rectangle by clipping it inside of the vertices. So for every single unprojected point inside of our vertice range, we're going to set its AABB rectangle, which is this one, which is basically a rectangle tool that we're going to clip towards. And we're going to first expand towards every single point. And later we're going to clip it towards the viewport, which with its visible rectangle too. So this I can actually hide it to show you what it does. Now let me just apply this function here. I think now it should be good to go. So if I comment that, and let's run the scene. And of course we did not update it. So we have here our rectangle tool, which being generated for all that information. We need to update its position, its size, and set its visibility to be true. And if the mouse position is inside of it, we're going to hide its visibility. So this should be enough to also update our 2D nodes towards the rectangle tool we built towards these functions here. So let's just run the scene. And as you can see now it's updated. And if we comment that line of code, you can see that the rectangle tool is actually escaping from outside of the window viewport. So that is why we clip that inside of the function. So if you want it like this, you can leave it like that. But I want to be inside of the screen. So that is why on the AAB collisions here, I have this code that the AAB rectangle is going to be equal to a intersection from the camera viewport visible rectangle 3D. So whenever it gets close to the screen, you're going to see it's going to be clipped and is not going to overlap out of the screen. And this is what it looks like. So this, I think it looks a little bit better, but of course you can tweak to your needs. And that is how we have the final step, which is to build this based on the AABB. Now, of course, the AABB we have displayed here is not the one that we are using for this one, because it's giving one in the local space, and if you want it, you can also update the code. So there we go. Now I'm going to show you one of the cool things about this is by editing the current panel styling to give a different appearance here to simulate what most games have. So let's reduce here the border width and let's not draw the center. So if I just run this, see the effect it gives, and I can actually update its border size here to something I want. And of course it does not update yet. So whenever we run, and you can see the effect it gives. You can also do a couple of fun stuff, which is to draw the center. And I think I did this by setting the corner radius. So we can actually as well disable this one if you wanted to give a new effect. You can also hide the blend value and update back to 1. And you're going to see the effect it gives. So as you can see, there we go. So yeah, a bunch of different things you can do with this, and it's a lot of fun to also do it. And there you go. These are one of the effects you can do with this AABB box. And you can also update this to be a 9-patch rectangle, so you can make some sort of crosshair, and you could do a bunch of cool stuff with it. You can also apply anti-aliasing, and also do something like a shadow effect to be around it. So yeah, a bunch of things you can do with just this simple effect. So that is why I think it's pretty cool to have it. If you want access to this main code, I'm going to leave it for members. So this is also quite important. If you are a member here on YouTube, you're going to get access to the full project. And if you are just wanting to follow this tutorial, I'm going to provide the link for this project as well. But however, I'm going to strip away all of the code you're going to see here. And I'm going to leave you with a blank starting point for this project. So you're going to have access to basically all of this stuff here, like the statue, the scenes, the materials, and the camera switch code. However, I am not going to leave any of the codes for the AABB. So yeah, that's about it. I also would like to mention how I got to achieve this effect, because it was quite a laborious process to research how to do this inside of Godot, as it was not easy to get on the first hand. So this tutorial was inspired by some research I tried to find on the internet. Various parts and bits I got inspiration from reading other people's comments and see how they were having issues with their code. So yeah, this is not a simple matter to resolve, and I needed to find help online. So I got a bunch of different code scraps from various different dates, and I actually found the codes that worked on my project, and also some inspiration for other people for the things that they want to do. So as you can see, examples of using that rectangle for the vertex mesh instead of the AABB, which you can also do. And this was all of the code that I found online. So yeah, this is what some people try to do, and also you can see for 4 years ago, and a lot of people have issues with this one, and I actually was able to get it to work. And as you can see here, this is because the AABB is a square one, and whenever it rotates, it's trying to update it based on the local. Yeah, so a bunch of issues and things that needed to do in order for me to find the code that actually work. So hopefully you found this tutorial useful, and you should now have some of the code that runs it. And as well, guys, I would like to ask your ideas and opinions about how you guys could support me in developing more tutorials and possibly other useful projects for you to use in Godot. Stuff like minimal viable products for game types and game systems, so you can use on your own. So I think I'm going to be opening a Patreon page, so you guys could support me there and get access to all these files. And if you also support me here on YouTube, you also get access to these files. And possibly I will also have a PayPal account, so you can also donate to me if you wanted to donate directly. And also this free project sample will be available on my itch.io page, which is where I keep most of the free stuff, so you can have access towards to it. So hopefully you found this video useful, and I'll see you on the next one.